This page from James Munkres' Topology text poses a classic mathematician's riddle. How is a set different from a door? The answer is that a physical door must be either open or closed, but a mathematical set can be open, closed, both, or neither. We are covering sections 17 and 18 of Munkres to identify closed sets, find limit points, and prove topological continuity. This tutorial requires a basic understanding of open sets as a starting point. To understand general topology, we must precisely apply these formal definitions, even when they differ from geometric intuition. This number line displays the closed interval AB. In topology, a set is closed if the area completely outside of it is open. Here, the regions from -infinity to A and B to +infinity are open intervals, confirming our interval is closed. If we shift to a half-open interval, including A but excluding B, the logic changes. The complement now includes the exact point B. Because this outside region is no longer strictly open, the original set is not closed. This leads to the definition of a closure. The closure of a set is the intersection of all closed sets that contain it, forming the tightest possible boundary around the space. Whether a set is closed depends on the openness of its complement, rather than the internal properties of the set itself. In topology, we need a way to define the boundary of a space without relying on measurable distance. Consider the interval from 0 to 1. A point is a limit point if every neighborhood around it intersects the set at another point. 0 is a limit point here. No matter how small its neighborhood becomes, it always overlaps the interval. However, a finite set of integers has no limit points. We can draw a neighborhood small enough to isolate the number 2 from every other point in the set. Theorem 17.6 provides a formula for calculating closures by looking at these limit points. The equation states that the closure of a set is the union of the original set and the collection of all its limit points. Limit points allow us to determine the boundaries of open sets by mathematically defining what it means to approach an edge. Topological continuity offers a streamlined approach compared to the epsilon-delta definitions found in calculus. A function is continuous if and only if the inverse image of every open set is also an open set. This diagram illustrates the pullback mechanic. If we take an open set in the destination space on the right and trace it back through the function, it must be open in our origin space on the left. Consider this identity function mapping the usual topology to the lower limit topology. In the lower limit destination, the half-open interval a, b is an open set. Tracing it back through the identity function leaves the set unchanged. But the interval a, b is not open in the usual topology. Because the pullback failed to produce an open set, the function is discontinuous. Alternatively, Theorem 18.1 states continuity can be proven if the inverse image of every closed set is closed. Topological continuity ensures the structure of a space is preserved when tracing sets back from the destination to the origin. You have now moved from basic open sets to identifying structural boundaries and continuous mappings. This summary guide distills the core rules for sections 17 and 18. Save a copy of these rules to use as a study guide. Test these skills now by attempting exercise 17 in Chapter 2 of the Munkres text. Ultimately, general topology analyzes the structure of a space by defining proximity through set relationships rather than using exact measurement.